Okay, our second speaker for this session is Karol Duda from Wrocław, University of Wrocław. So who'll be talking about torsion subgroups of small cancellation groups.
Thanks. So before I start talking about small cancellation, I will start with some motivation of my work. Today's look at it's the conjecture by Norin, Osada, and Chititsky that says that every action of a finitely generated torsion group on a finite dimensional cut-zero complex is elliptic. In the paper where they stated that conjecture, they also proved it for two-dimensional cut-zero complexes. And that's some property that was already known for cut-zero cubical complexes before. And how do we get to small cancellation from cut-zero? And that's because we have the following meta-conjecture that this property is not something related only to cut-zero, it's something more general in non-positively curved case. So there's this meta-conjecture by Karol and Osada that states that every locally elliptic action on a finite generated group on a finite dimensional non-positively curved complex, whatever non-positively curved complex here means, is elliptic. And locally elliptic action is an action in which orbit of each group element is bounded, and elliptic means that orbit of the whole group is bounded. But in the cases that we will consider, it's less difficult, and locally elliptic means that each group element has a fixed point, and elliptic means that the whole group has a fixed point, so there's a global fixed point for all elements. Okay, and there's also the question by Svensson whether a group acting properly and co-compactly on a cut-zero space can have an infinite torsion subgroup. Okay, so let's go to this meta-conjecture case and what are exactly these non-positively curved complexes that we would like to prove? So obviously cut-zero, but also helicomplexes, where helicomplex is complex satisfying property that any family of pairwise intersecting combinatorial balls has a non-empty intersection. Small constellations of the ones that we'll talk about today for C6, C44, and C36 conditions. Those values are the ones where small cancellation gives us non-positively curved complexes. We also would like it for systolic complexes, which are simplicial complexes such that star of any non-positively curved vertex in this diagram can be replaced by some triangulation without internal vertices, and quadric complexes, which is analog of systolic complexes, but for square complexes. Okay, so I can tell a little about small cancellation. And we are in simply connected case here, so definitions are slightly easier in than full generality. But less still, the crucial definition for small cancellation is definition of piece. Piece is just a non-trivial path that exists in at least two distinct two cells, and it exists in their intersection. So if we take a picture like here, so we have two cells, then piece can be this part, but it can also be some shorter fragment of it. And first of the small cancellation conditions, the city condition means that for a complex that there's no two cell whose boundary can be covered by fewer than p pieces. So if we take, for example, such a complex, then you can see that there's only one two cell whose boundary can be fully covered by pieces, this internal one, and we have 5 pieces here, so this complex satisfies C5 condition. But if you add two cells like that here, then this complex no longer satisfies C5, it only satisfies C4 because 3 of the previous pieces are covered by 2 new ones. The second condition, TQ condition, says that there are no these diagrams in this complex, which have internal vertex of valence between 2 and q. You can obviously see that T3 condition means nothing. But that's why we do not even write it in C6 case. We just consider C6, not C6, T3, because T3 means nothing. So, for example, such a complex would satisfy T4 condition, but we add some two cells like that, and this complex also satisfies T4. That's because it is defined for disk diagrams, and all disk diagrams with internal vertices in this complex would have this internal vertex of valence 4. Okay. So as I said, cases that are important for us are C6, C4T4, and C3T6. And that's because they are non-positively curved, and I will show it by showing examples. And like usual example of C6 is just tessellation of plane by hexagons. Of C4T4 is tessellation of plane by squares. And C3T6 is tessellation of a plane by a triangle, equilateral triangles. Okay, so I talked a little about small cancellation complexes, but the topic was about small cancellation groups. So what are small cancellation groups, or rather groups with small cancellation presentation? And those are groups whose Cayley complex satisfies the CP and TQ conditions. And for example, if you take 3 abelian group on 2 generators and its standard presentation, then it will be C44. Okay. So after this introduction, I can finally talk something about my results. And the main result is the following theorem. It states that for any simply connected small cancellation complexes that satisfies those non-positively curved small cancellation values. And if we have a group acting on such a complex by automorphism with the assumption that the action on the one skeleton is free, and if the action is locally elliptic, then it is elliptic. So you can see that this assumption of the freeness of the action on one skeleton is quite strong. But even with that assumption, we get some significant results, namely that torsion subgroups of groups defined by small cancellation presentations are finite cyclic. And this result is already nice, but it also has some applications about automatic continuity. And that's because we have that property about automatic continuity that happens for any finitely generated systolic, Heli, or cat0 groups, which torsion subgroups are arctinian. And C6 groups are systolic groups, C4T4 groups are Heli groups, and C3T6 are cat0. Well, at least as long as they have finite presentation. And by theorem 2, they all have finite cyclic torsion subgroups, so the torsion subgroups are arctinian, and thus we get this result. So I would like to know something about the idea of the proof of theorem 1, but only in the C4T4 case, because it's the easiest one and I won't have time for the other ones, I guess. So we begin by showing that each group element F fixes exactly one 2-cell in the complex. And that follows from the assumption of the freeness of the action on the one skeleton. Because if we assume, if we would have two cells that are fixed by this group element, then we could find something that is between them that is also fixed. And at some point we will get either vertex or an edge that will be fixed by this group element. And after that, we need to show the following formula that basically says that for any group element, we can find a power which moves everything far away in the boundary of this the fixed cell that is fixed by this element. And we need such powers for the last part of the proof, that if we take two elements that fix two cells, then we can construct element of infinite order. And if we construct an element of infinite order, that it cannot fix anything. And we assume that it is locally elliptic. So every element fixes a point. So we have some problem, some contradiction with G. So we couldn't find, it wasn't possible to find such two elements in the first place. Okay, so let's go in more detail about the steps 2 and 3. So first, in step 2, we first need to observe that if G acts freely on the one skeleton, then these elements in the group that fixes some two cell, then it acts by rotation, and the rotation has some finite order. We claim that for either even or odd m, we can just use this formula, and such power would work as required. And that's because if it doesn't work, then we have one of those situations. So we have this cell FF, we have some cell F prime. In small cancellation, it is that this intersection would either be a vertex or a piece. So we have some piece, and the image by this f to the power of k is moved in such a way that we have non-empty intersection. But we are in either this case or this case because of the choice of the k. And we are in C4T4 small cancellation complex. And we clearly can cover, in this case, the whole boundary by 2 pieces and by 3 pieces in this case, in the odd case. So that cannot satisfy C4 condition. So that's step 2. And step 3 is that we have those two cells, F and Fg, that were fixed by F and G. And first, we want to find smallest, I call it gallery. So the sequence of two cells, that consecutive cells have non-empty intersection, and want it to be, as I said, the shortest one. So we have something like that. And we want to show that if we take this F to K, G to L, and if it has finite order, then it will be some closed subcomplex in complex X. So at some, obviously this has finite order, then at some point we will just land with the image of this cell on again on this cell. So we will get some picture like here, that it was closed after some iteration. And if we have some picture, then we have closed path here. But the complex X is simply connected. So we have Landon Van Kampen lemma, which states that there's a disk diagram inside. And if there's the disk diagram here, then we can count its curvature. And I think that now I should talk a little what the curvature here is. So if you take a positively angled disk diagram, positively angled means that for every corner of each two cell in the diagram, we assume that there's some angle there, and it's positive. And if you take some vertex of this diagram, then we can define the curvature by taking the following formula. Take 2 minus Euler characteristic of the link of this vertex times pi minus sum of the angles of the corner containing V. And I think that it's good to show some example of that. So let's take this diagram like here and assume that red corners have angle pi over 3 and blue ones have angle pi over 2. Then this vertex as curvature pi over 3. Why? Because link of this vertex have Euler characteristic 1. So we have pi minus sum of the angles. In case of this vertex, we have Euler characteristic 0, no 2. So we count it by curvature by taking 2 pi minus sum of the angles. And in this one, Euler characteristic is 2. So curvature is 0 minus sum of the angles. Okay. And why we need this curvature? Because there's this combinatorial Gauss-Bonnet theorem, which, well, it has some more generality, but I assume here that each two-cell is regular polygon, so we do not count any curvature of face of two cells. We only have curvature of vertices. And if we take positively angled this diagram with this assumption, then the sum of the curvature of all vertices is equal to 2 pi. So we are in this case again. So we have this diagram in this small cancellation complex. I assume that it's C44. And we have to show that if this complex was closed, then this diagram should have curvature 2 pi if we take a sum over all vertices in this complex. But this small cancellation complex, and this diagram will take minimal area 1, then all internal vertices have non-positive curvature. So all positive curvature is at the boundary. And now we have properties of this gallery that if you take a sum of all vertices along this gallery, then it might be positive, but it's not very big, it is bounded. In C44 case, it won't exceed pi over 2. And the choice of this power that was of f that by step 2 was to have the following property, that if you take sum of the vertices along the fixed cell, that sum has to be non-positive. And moreover, there is something that I didn't mark here on the picture. If we have that sum over this gallery is positive, and this one is positive, then the choice of this power of f will guarantee that if you take sum over curvature of vertices along this two cell between them, this fixed cell between them, it will be negative and it will cancel one of these positive curvatures from these galleries. So you'll never exceed positive curvature of one gallery that was bounded by pi over 2, so that this diagram cannot exist. And that's the end of the proof of theorem 1. Still have some time, so I will talk how theorem 1 implies the second theorem. And that's thanks to theorem of Heutschmann, that says that if you have a group with small cancellation presentation and take some element of finite order, then it is necessary conjugate of a root of some relator of this presentation. And now if we look at the situation in theorem 2, we have torsion subgroup of some group G. So the action of it on one skeleton of G, of the Kelly complex of G is 3, because action of G on its Kelly complex is 3 on one skeleton. And by this theorem, each element of this torsion subgroup is conjugate to root of some relator, and all two cells are relators. So each element of H fixes some two cell. So the action is locally elliptic, and we can use theorem 1, and the action has a global fixed point. Now, and now we have the situation that all two cells are finite, obviously. So since the action was 3 on the one skeleton, then the only option for H is to be a finite cycle. And I guess that's all. Thank you for your attention. I will also show some literature about this. The paper about C44 case is available at Archive, and I think that the paper that considers all three cases should be available soon as well.
Okay, let's thank the speaker. Okay, so we have quite a bit of time for questions. Does anyone have any questions? I'll just wait a little bit, make sure, because last year I think I didn't wait too long.
So I think there was a conjecture at the beginning where you said that like group acting on cat0 properly, completely, something like that. Can have infinite torsion. But I think there is a. I guess you want finite dimensional or something.
Yes, I think there should be finite dimensional here as well.
And
that was the problem, why finite dimensional is also in these conjectures. Yes, I think there should be finite dimensional here.
So I think they counterexample, but I'm not quite sure if there's an intuition why it goes wrong with finite dimensional. So
I did not understand. No.
So
can you repeat?
Okay, is there any counterexample, or is there an intuition why it should go wrong, or and why it should be better for finite dimension?
Well, there was some example in finite dimensional case, but I cannot remind it. In infinite dimension, there was some problem why we assumed finite dimension. There was a counterexample, and okay. I think it's available in this work of in this paper of Heteloside that is available at Archive. They mentioned it, that there's some counterexample if you don't have finite dimensionality, but I don't remember what it was exactly.
Okay, I have it then. Thanks.
Do we have any other questions from the audience? Okay. So this talk is about small cancellation C4T4, I think.
Yeah, in this talk I only talk about C44.
Are there any other interesting results about other types of small cancellation besides if you put a number besides 4 there?
Well, there. That's
okay. Yeah.
What's interesting?
It's a very open-ended question because, well, yeah.
There are some other cases. Obviously, if you have like for these values, you take C7, then everything becomes hyperbolic. So you just get to more interesting things there by just hyperbolicity of the complexes. And there's also this metric condition C prime, and there's some other results there. And there was some attempt on making them all those small cancellation complexes, whether they are can be cubulated. But there's then it shows some weird condition to do that, which is something between C prime and C, when it is half of some condition, half of some condition, and then you can show something about cubulating CA groups, but you cannot do anything in the full generality except for C36 when you can show that they are zero. And I don't know what what's exactly interesting for.
What I was sorry. What I was kind of maybe trying to ask is like, can you say anything more about torsion subgroups, like for example, C6 or?
Yeah, for C6, this is very similar in proof. It's actually the point is that you cannot make second step work as well as in C44. It's that you get additional condition because, well, that's a translation for C44 that everything is moved far enough. But in C6 case, I think I will use this picture. You can have situation that you are moved. Well, in C44, this far enough means that I'm going from here to here, right? So I'm going far. If I'm getting this one gallery, then the next one will be far away. But in C6 case, if I go from here, then I'm not really able to force that I'm going on the other side of this two-cell, because it's possible that the torsion subgroup acting here, the torsion element acting here has order 3. So I'm going from here, and then to this gallery. And in that case, if I would go like that, then I would get first element and I could close it, right? So at this point in the proof that we show that we either can force this element to add some power to move everything far away, or we are in the case where each element has order 3. And then get free Burnside group, which is finite. So that's the difference in the C6 case, that this part is more difficult because on one hand, it's more difficult than this proof that was here to show this part, but there's also this special case where everything is just of torsion free. Well, it's of order free. Torsion free is a tricky thing to say.
Thank you. So I think this might be, we might need to move on to the next speaker now. So thank you. Let's just thank the speaker once more.